You've not done the 3 variables that we're about to get to. So, part A I ask you to do by substitution. Part B I ask you to do by elimination. Are we familiar with those words in general? I know you probably forgot what they are, but do you remember those words? Yes. Okay. Substitution is when you solve for a variable. What one you choose to solve for is up for debate, although this one's pretty obvious, and I'll explain that in a minute. You get a variable all by itself. Something will say x equals 2 plus y. And once you know what x equals, you can use that other quantity, since it equals it, to substitute in, right? You take something out. It's like taking out a 4 and replacing it with a 2 plus 2. That's legal, right? 2 plus 2 equals 4, right? So if you took a 4 out of a problem and replaced it with a 2 plus 2, does that make sense? So in this particular case, you want to solve for a variable first. And you've got 4 options, this x, this y, this x, or this y. The one that makes the most sense, because it's not going to require much work, is to solve for which one of those? The second y. Because there's no coefficient, so I don't have to divide anything away. I can literally just subtract 2x. And really, I'm changing that second equation to negative 7 minus 2x. So that's almost like the new second equation. It's a rearranged version. I like it because now I have something that's equivalent to y. So I now have something that can replace the other y in the problem. Since y equals this, I can go and replace that y up there. So I get 3x plus 2, and then I'm taking out the y and replacing it with this equivalent binomial. And so now I have one equation with only one variable in it. You see, when I started this problem, I had 2 individual equations, each of which had 2 variables. It's impossible to take one equation with 2 variables and solve it. That's impossible. Because there's a lot of different x and y combinations that would work for the first equation, and there's a lot of x and y combinations that would have worked for the second equation. But there's only one x and y combination that would work for both, and that's what we're after. So the substitution allows us to get this down into one equation with one variable, and now we can solve for x. So we're going to distribute our 2. Combine like terms, and add 14 to both sides. And again, we're looking for the one XY combination that's going to work for both equations. Did I do something wrong?
Yeah. 2 times 2.
Oh, you guys. I was never really good at math, so thank you for keeping me on my toes. So it's negative x. Oh, good. It doesn't really change much. Negative x, and then x equals negative 5. See? 20 kids. Built-in auditors. It's fabulous. Okay. So again, we're looking for the xy combination that works for both equations. Well, we've settled on what x is the right x. Now, you can take that x and plug it back into the first equation to find the appropriate y. Or if you plug it into the second equation and find the appropriate y, it should be the same y no matter what. Although it probably makes the most sense to go back and plug it into this equation, because then we don't have to really do any solving thereafter. You can just plug it in, crunch the numbers, and be done with it. So y is going to equal negative 7 minus 2 times that negative 5 that we now know. And negative 7 plus 10 is 3. There's our solution. Now, these functions, and I call them functions because there's x, y's in them. What kind of functions are they? You only know about 3 functions: linear, quadratic, and absolute value. Linear, yeah, because there's no x squared. Linear, linear. So if I were to graph this line, you can't really graph it until you solve for y. Do you guys remember that? Right? And then graph this line, they would cross there. I'll just show you quickly. So y equals, that's going to be a negative 9 minus the 3x over. I'd have to subtract that 3x over, and then I'll have to divide that whole thing by 2. That's going to be the first line. The second line, I just have to, well, I already solved for y, so negative 7 minus 2x. Graph. And guess what? They cross right around there. Now, on the graph, it's hard to see exactly where that is. But again, we have a favorite menu, second trace. Second trace, which option makes sense for what I'm looking for? 5, where they intersect. So it's going to ask me for the first curve, and right now it's got the cursor on y1, which that's one of the curves I'm looking for the intersection of. And then the cursor jumps to y2. Yep, that's the second curve I'm looking for. The only reason you have to select your curves is because it is possible to have 10 different equations in there, and you really can only find where 2 cross at a time. Does that make sense? So, but normally you'll only have the 2 in that you look for, so you can just hit enter, enter, and then guess. You always ignore enter. Negative 5, 3. Okay? All right. Elimination. This is going to be more, I'll be honest, we're not going to do substitution much at all for the 3 variable type of system we're learning about today. We will do substitution more this year when we get on to different function types, but for 3 variables, we're doing the elimination. What we're about to do is going to be a better reminder for what we are about to get into. Can you open the window for me, please? Is it hot in here? I feel like it's really warm. Okay. I'll also open the door. So elimination is a little bit different because we don't want to solve for a variable. In fact, we like B just the way it is set up because the x's are lined up above the x's, the y's are above the y's, equals, and the constant numbers are on the right side. If it's not already lined up, you do need to rearrange it to get it lined up like this. Are we clear with that? Okay. Now, with elimination, you're going to either add your equations together or subtract them from each other in order to get one of the variables to eliminate. We're not quite ready to jump right into that addition or subtraction of the 2 equations yet, though, because what has to happen first so that one of the variables truly does eliminate is what? Does anybody remember? Chris?
Like you would multiply by negative 2 on the bottom to make it plus 2y, negative 2y cancel out.
Right, so you have to choose either to get your x coefficient the same number, which you'd make those both 6's if you chose the x. Oh my gosh. I'm sorry. I should just throw it out and go one-eyed like a pirate all day. You could multiply this by 2 and this by 3 to get those both to be 6's. Or what Chris just said is this is a 2y. You could multiply this by negative 2. Now, Chris, it sounds to me just based on the fact that you just said negative 2 that your algebra teacher taught you to always make them the opposite sign. Mm-hmm. Is that true? Which is one approach. And if you always make them the opposite sign, one's a positive 2y, one's a negative 2y, then if you're Chris, you will always be adding your equations together. Because adding a positive 2 and adding it to a negative 2 is what's going to make it a 0 and cancel, right? I do allow it and teach it a little bit differently. You can get them to be opposites, or you can just get them to be the same number, whether they're both pluses or both minuses, that's fine. So I'll just show you my way. Which would be multiplying this by 2. Now you have to, one of the big things you have to remember is that every expression in that second equation has to get multiplied by 2. So the 2x becomes a 4x, the y becomes a plus 2y, and the negative 7 becomes a negative 14. Now my rule is this. If it's the same sign, subtract. There's a little alliteration there. Do you guys know what alliteration is? Same sign, subtract. Okay? If they both have the same sign, whether they're both positives or both negatives, they're the same number, so subtracting anything from itself will cause it to eliminate. Right? It'll be gone. It'll be 0y. It won't be there. You with me? So same sign, subtract if you want to do that. And if and when it comes up, opposite signs, add. If your Algebra 1 teacher got you in that habit that Chris's obviously did of always making them opposite, one positive, one negative, then you guys will always add the equations together. Whereas I am going to have to subtract here. And when I say subtract the equations, because I have seen this mistake a gazillion times, I don't just put a minus out in front, because then people forget about that, especially when duplicate signs come up. I put a negative in between every single one. So 3x minus 4x is negative x. 2y minus 2y is gone. Equals negative 9 minus negative 14 is negative 9 plus 14, which is 5, and divide by negative 1, and we are at an x equals negative 5. Did you guys notice that these are the same system twice? I'm just showing you both methods. Okay, and then just like the other one, we're looking for the x and the y when you're solving a system. So I need to find the y coordinate, which I can go back into either one of the originals, would probably be the best option. I'm going to go into this one because there's less work. 2 times an x of negative 5 plus y equals negative 7. I'm going to solve for y. So right now I have a negative 10 on the left. So I'm going to add 10 to both sides. Y equals 3. And since these are the points at which the functions cross, it is most common to see your answer written as a coordinate pair. Do you remember that? How'd we do? Okay? All right. Now, 3 variables. It's going to be a lot of organization is going to be key here. So I want you to write everything exactly the same way I write it. So like I said, we're going to be doing elimination. So we have a choice, and you want to pick what's easiest. Is it easiest to get the same numerical coefficient on the x's, on the y's, or on the z's? The z's, because it's already done. Yes? I mean, not necessarily by your method, Chris, but by my method, it's already done. 1z, negative 1z, negative 1z. They're all ones. I don't care about the pluses or minuses, because I'll address that issue when I make this decision. So I don't need multipliers like I needed a multiplier up here, and I had to rewrite it. I don't need that. So I'm just going to go through the first 2 equations. And since on my z's I have opposite signs means do I add or subtract? What? Same sign, subtract, opposite signs, add. So I'm going to do plus, plus, plus with the first 2 equations. 2x plus 6x, 8x. 1y plus negative 3y, negative 2y. 1z plus negative 1z, eliminated. 15 plus 35, 50. Then I'm going to do my second 2 equations. Am I going to add or subtract these? Right? They're both negative z's. Same sign, subtract. I'm only looking at the signs, by the way, on the variable that has all the same number in front of it. That's going to drive my decision. And I do that for everything. So same sign, subtract. So subtract, 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 subtract. 6x minus negative 4x. 10x. Negative 3 minus 4. Awesome. Negative z minus negative z. Gone. 35 minus negative 14. Beautiful. Now, do you see how I've pared this down to now more of a traditional system? Now it's 2 equations, 2 variables. 3 equations, 3 variables. Just got pared down to 2 equations, 2 variables. And now, again, I've got to redecide. Is it easier to make my x's both the same coefficient or my y's? And here, I truthfully don't think it matters. These 2 could be made of 40, or these 2 could be made of 14. Does anybody care? I'm going to make them both a 40. So this gets multiplied by 5. That's going to change that to 40x minus 10y equals 250. And the second equation to make that a 40 has to get multiplied by a 4. That's 40x minus 28y. And 49 times 4 seems like a good time to use the calculator. 196. And the numbers can get big. We're good with it. We got a calculator. Now, there's my 40s. Same sign subtract or opposite signs add? Same signs. They're both positive 40s. Subtract. Subtract, subtract, subtract. 40 minus 40, gonzo. Negative 10 minus negative 28. What'd you say?
18.
18 what? 250 minus 196. 54. Divide both sides by 18. Y equals 3. Now, it's a domino effect backwards. I can't go back to the original. If I go and plug in a y of 3 to any of these, I still have x's and z's, x's and z's, x's and z's. I've done 90% of the work. I just have to go back and get this other 2 parts of the answers. I got to find what x equals still and what z equals. So I go back to my previous layer, and I can go to either one of these equations, and if I know y, I'll do the top one. 8x minus 2 times 3. That's a minus 6, right? So I add 6 to both sides. I get 8x equals 56. Divide by 8, x equals 7. And now I go back, domino effect, to the beginning. Either one of those initial 3, I'm going to pick the first equation just because I like the smaller 2. So 2 times my x of 7 plus my y of 3 plus my unknown z equals 15. So right now, what is all this? 14 plus 3 is 17. So I'm just going to subtract 17 from both sides, and z equals negative 2. Okay? Organization is definitely key here. Keep it neat, keep it clean. Life is good. Okay? Any questions? Okay, let's flip over. And usually when we've seen these problems on the Regents, they've been pretty straightforward. Look at exercise 3, look at exercise 4. It'll just be exactly the model that we went over in the previous example. The only real application that this will come up in is a situation like this one. Write the equation of a quadratic function that contains the points negative 1, 6, 1, 2, and 2, 9. Now, this may be a little bit premature because we haven't restudied quadratics yet. But in general, you guys should be familiar with this quadratic format. ax squared plus bx plus c, right? You use that a lot with the quadratic formula to identify a, to identify b, to identify c, and then you use the quadratic formula. Well, right in this particular problem, we don't know a, b, and c. What we do know is an xy pair that will make that true, another xy pair that'll make that true, and another xy pair that'll make that true. What's that? That's going to give us 3 different equations with the 3 variables a, b, and c. So I'm going to come up with my system, I'm going to plug in xy, so a y of 6 and an x of negative 1. Whoops. And when I simplify that, and I'm going to put the equals 6 on the right-hand side. Is everyone okay with that? Just because that's usually what they look like. So what's negative 1 squared? 1, so that's just 1a. I'll just leave it as a. And then we have minus a b plus a c equals 6. There's one equation, 3 variables. Well, that's not solvable. We need a second equation. So we plug in 1 and 2. 2 for y, 1 for x. And that's going to clean up to a regular a plus a b plus a c. And the last equation is going to come from, because we still only have 2 equations but 3 variables. You need 3 equations, 3 variables to make something possible. So we're going to plug in 2, 9. 9 equals a times 2 squared plus b times 2 plus c. That's going to give us 4a plus 2b plus c equals 9. So from here on out, now it will be the same type of system we've been solving before. So now we can pretend like we're at the beginning of the problem as far as solving a system is concerned. Which variable would we like to have the same coefficient in front of all of them? C, right? Not even a debate because it's already done. 1, 1, and 1. Okay? So, no multipliers needed. I'm going to do these two. And am I going to add or subtract those? Subtract. Same sign on the C, so subtract, 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 subtract. A minus A. Gone. That's a coincidence, right? Because we didn't design this for our A's to eliminate. We designed it for our C's to eliminate, correct? So that's actually a nice coincidence. It's going to make this a little bit easier than the other one. Negative B minus B. Negative 2B. C minus C, that does eliminate. We planned that. 6 minus 2 is 4. So what happened here that doesn't usually happen is usually where we have 2 variables left, we already can solve for B. I'm not going to do it yet. I'll do it in a second. I'm going to go on to this next one. Add or subtract? Good. 1A minus 4A. Yep, negative 3A. B minus 2B. 1 minus 2 is negative 1B. C minus C is gone. 2 minus 9? Negative 7. So normally I'm left with an A and B equation and another A and B equation, and I have to repeat elimination. I'm lucky here because I can jump right into figuring out what B is. Divide both sides by negative 2, and B equals negative 2. I can now take that and go into this equation. Negative 3A minus a negative 2 equals negative 7. The double negative is negative 3A plus 2. And then I solve. Subtract 2 over. Divide by negative 3. And A equals 3. But I had 3 variables. So now I have to go back to any one of my originals. The top one's probably the easiest. A of 3 minus a B of negative 2 plus an unknown C equals 6. Well, 3 plus 2 is 5, right? So if I subtract 5 from both sides, I am done. C equals 1. Now remember, this equation this question didn't start off as, hey, solve the system. Right? It was a system question, essentially, but it didn't say solve the system. It said write the equation of the quadratic. So now that we know A, B, and C, we're going to take that and we're going to replace A with 3, B with negative 2, C with 1. And that's your answer. And I will show you just for fun, really, so you can make the connection and you just really appreciate math as much as I do. I type in the function, I take a peek at the table, and you'll see those points on there. There's negative 1, 6. There's 1, 2. And there's 2, 9. Capiche? Good stuff. All right, you guys picked up your spiral on the way in.